Hey, thanks for joining us for this last video in Chapter 7, where we're going to talk about the competition that exists among the four different types of leaving group reactions that we have discussed, SN2, SN1, E1, and E2. Because the reality is, right, like chemicals don't know that maybe you've intended for them to do SN2 reaction or SN1 reaction. They're going to do what they're going to do. But often the reaction pathway that they choose is not so clear cut, right? Because they don't know that they're created to do an E1 reaction or something like that, right? So there's going to be sort of competition among different potential possible reaction pathways. It's kind of like this game you might have played. Not some of you might actually play this in your dorm, and no judgment there, but where like four different reactions are competing for the molecules that might go through their pathway. Okay, so we're going to kind of do a summary of everything that we've discussed to be able to really predict what the preferred product might be. And so we're going to look at, of course, the nucleophile or the base species. Often that is one and the same. Basic compounds species are often nucleophilic and so forth. So we're going to call this the attacking species. And then, of course, nothing is going to happen without the leaving group containing substrate. Now, yeah, and by the way, in the future, we're going to be looking at reactions where there's not like a leaving group. That's not a requirement for organic reaction. But so far, the first reactions you guys have learned have all involved leaving groups. That's been the theme between Chapter 6 and 7. Now, other factors that could matter that we've discussed, of course, is solvent. And then, of course, the temperature matters, and then you get to the product, right? So the idea here is that we want to be able to predict this. Right, that's the idea. Okay, and we're going to look at these 5 different things. The attacking species, the substrate, and then the leaving group in specific, and then the solvent, and the temperature. Okay, those 5 factors. Okay, and hopefully it's just all review. Okay, and again, apologize for I don't know why the symbols don't show up, but this was supposed to be just like a dot. So if the attacking species is a good, strong nucleophile, but not that weak, not that strong as a base, for example, cyanide is somewhat basic, but it's not a good base per se. And iodide is a very good nucleophile, but it is not at all basic. And so same thing with phosphines. Here's triphenylphosphine molecule. These are great nucleophiles, but not very strongly basic at all. In that case, the preferred reaction is going to be, hopefully this is not surprising, it's going to be SN2 reaction, right? If you have a great nucleophile, but they're not gonna do good as bases, SN2 is preferred. Not surprising. Okay. Now, what if you have a strong nucleophile that's also a strong base? What are some examples? Well, alkoxides that are not bulky. Maybe we'll say slim alkoxide. Or alkynide. Remember, alkyne has the triple bond, and then if you turn that alkyne into an anion, that becomes an alkynide ion. Remember that "ide" ending means anion. Now, these can do both SN2 as well as E2 because they're strong base. So you're going to see competition between those two. Okay. Hope that makes sense. If you have a strong base that's not great as a nucleophile, that often means they're like just bulky. Okay. So maybe we'll make that note here. So here's an example. This is often abbreviated lithium diisopropylamide, and I'm not showing the lithium part because that would be sort of the counter, spectator ion. T-butoxide is a great example of bulky alkoxide base, or tertiary amines like triethylamine. There's a good base but not great as a nucleophile because of the bulkiness. These often promote the E2 reaction. Now, I want you to notice so far, as long as you have some strong attacking species of some sort, you're going to see basically SN2 or E2. Okay. If you have a weak nucleophile / weak base, basically if you don't have any good nucleophile or a good base at all, like all you have is water, which is a weak nucleophile, or alcohol or something like that, then you're going to see the competition between SN1 and E1 happening. Why is that? Because these are the reactions that are not initiated by the attacking species. Remember, that's SN1E1 is the one that's initiated by the substrate by itself. The leaving group leaves, and then that starts the sort of cascade of mechanisms that lead to the product. Okay. Maybe one note here about SN1, all else equal, SN1 is often slightly favored over E1 slightly. Okay. As a rule of thumb. Okay. Now let's think about the substrate. So this factor. That substrate, of course, could be tertiary, secondary, or a primary, right? A tertiary, right, like an example would be something like that. That's a tertiary. Secondary would be like that. Primary would be like that. But then what happens? Well, tertiary substrate is good at giving you a stable carbocation, as you recall. And for that reason, it often promotes SN1, E1, of course. And then they definitely cannot do SN2 because this is too bulky for nucleophile to attack, if you recall. But it could do E2 reaction, so it would be a competition among those three. Maybe I'll use this slash just to be consistent. Okay. What if you have a secondary, right? Then it can form a carbocation. It's not as stable as tertiary, but it can be formed. It can be formed. Secondary carbocation is potentially a thing. So, and then it's not so bulky that this could be attacked by a nucleophile directly to do SN2, and so for that reason, this is really the most sort of complicated situation because you could do SN1, E1, E2, or SN2. Any of those is possible with secondary substrate. With a primary leaving group, it would form a totally unstable carbocation if the leaving group left on its own. So basically carbocation is out of the picture, and so for that reason it cannot do SN2 or SN1 or E1. Remember, those require a common carbocation intermediate, and so for that reason these are the only two viable pathways for primary. Okay. If you have, this should have been up here, maybe I'll just add it in. If you have a methyl, right, then that definitely is not going to be a carbocation, and it cannot do elimination because well, there's no other carbon to eliminate with to make the double bond. To make a double bond between carbon and carbon, you need another carbon, and so for that reason the only thing that this can do is SN2. Okay. Now let's think about the leaving groups. Okay, so one of the things we could note is that SN2, E2, E1, SN1 all benefit from having a good leaving group, because they all involve a good leaving group. So that's kind of across the board. So that I know that doesn't help us distinguish, but that's a fact. One slightly differentiating factor that we could talk about is SN1 and E1. Remember, the rate determining step is when the leaving group leaves on its own unimolecular, and that's all that it depends on, right? And so as far as the likelihood of the reaction happening, so these reactions solely depend on the leaving group's ability to leave. And so for that reason, if you have excellent leaving groups, that they tend to speed up the SN1 E1 more than SN2 E2. Okay. Slightly. Maybe I should add slightly more. So all right. So that's all we could say about the leaving group. So they don't really, it's not a huge differentiating factor. A solvent is not also as big of a differentiating factor. I would say the attacking species and substrate are the biggest factors. These have a higher weight than others, I would say. The solvent, right, we talked about they do matter. There's some solvents that would be good for SN2 and E2, and some that would be good for SN1 and E1. Okay, remember that SN2 really depends on the strong nucleophilicity of the nucleophile, and kind of similarly E2 depends on the strong basicity of the strong base, and so for that reason polar aprotic, and if you don't remember what that means, you should check out the notes from chapter 6. Because aprotic solvents that are polar, they don't solvate the nucleophiles to dampen the nucleophilicity or the basicity of the attacking species. So that is a good thing for SN2 and E2. Now, I would say the solvent, it's not gonna, like a make it happen if the reaction is unlikely to happen based on the substrate or the attacking species. This is what this says is polar aprotic solvents tend to get out of the way of the attacking species doing their job in SN2 and E2. That's sort of what that means. Now, as opposed to protic solvents, more actively get involved and they actively lower the nucleophilicity, right? Polar aprotic solvents don't necessarily enhance the nucleophilicity, it's just that they don't lower the nucleophilicity or the basicity. Protic solvents, on the other hand, lower the nucleophilicity and basicity. Why? Because remember, the protic solvents have a proton like this on a heteroatom that has a fair bit of partial positive charge. And remember, the nucleophile or a base often has partial negative charge or full negative charge. And so for that reason, if you have that sort of hydrogen bond to nucleophile or the base, this gets its electron density gets lowered because some of it gets donated to this partially positive proton, right? So it lowers the nucleophilicity. That's called solvation. It's bad for nucleophilicity and basicity. So it sort of disfavors SN2 and E2 for sure. And protic solvents can act as a weak nucleophiles or bases, and also they can solvate. I didn't add this, but once the leaving group leaves, they can be solvated by the protic solvents. And so all that together, we could say that protic solvents favor SN1, E1. Okay. Hope that makes sense. Last factor here is temperature, and you probably recall because of the Gibbs free energy equation, where entropy factor is multiplied by the temperature, and so for that reason, right, the higher temperature favors elimination reactions. Because in E1 or E2, right, if you have a leaving group plus base, the product, you have the product alkene, the leaving group that left, and the base that picked up the proton. So you have three species, which makes the delta S positive, whereas in SN1 or SN2, the number of particles do not increase, remains the same. So the delta S is basically 0. And so, right, the temperature doesn't really affect that much, whereas temperature would affect elimination reactions more favorably. So if you're heating it up, often these reactions are favored. Okay, hope that makes sense. And one thing I kind of forgot to say about the substrates here, right, if you have a very bulky specific, like very bulky bases, I should say that the maybe I'll add of the CHP7e product. With a skinny, strong base. CHP7e products are favored, and Hoffman products favored with bulky, strong base. Example of that, sorry, I don't have a good space to draw that, but is like if you had something like this, and let's say you have methoxide and heat, or t-butoxide and heat. With methoxide, the base is able to get into the middle, taking proton from here, so the CHP7e product forms. Whereas with really bulky base, right, often it's not able to get to this more hindered proton, and so it'll grab the proton from the end, and the Hoffman product forms. So this is CHP7e. This is Hoffman. Okay, and in class next one, I don't know if it would be next time or next week or whenever, we're gonna do some practice with applying all these principles to predict the product. Okay.